We physicists have waited 100 years since 1916 for this photograph.
It's an area, one of the universe's most intriguing and enigmatic occurrences may well be black holes. Although they are essentially invisible to us, they are enormous creatures in terms of power. Imagine a black hole that has a mass that is between 2 and 4 million times that of the Sun. We now know progressively more about them up close and personal, having learned nothing at all about them before thanks to the study that has been done on them over the past few decades. Even if everything has only gotten stranger, Michio Kaku recently said that we have at last seen what is within a black hole. The scientific community may have overlooked some features up until now, but these new findings shed light on them. Come along as we explore black holes further and see what lies within the largest object in space. Prior to delving into the specifics of Michio Kaku's discovery, it is necessary to discuss firsts. There are still certain gaps in our understanding of black holes, despite the fact that the majority of us have a basic understanding of them. You know, black holes were predicted to exist when Albert Einstein published his general theory of relativity in 1916. Black holes were only theoretical concepts at the time. The scientific community didn't discover proof that black holes exist for another 50 years. This occurred in the 1960s when they discovered an unusually brilliant blue star that was releasing X-rays while researching the Cygnus constellation. This star was orbiting a massive dark object rather than being a stationary object. The term black hole came from the discovery that the X-rays were being drawn into the black object they were circling rather than just traveling about on their own. This finding was important because it demonstrated that black holes are real phenomena and are not the product of Albert Einstein's crazy imagination. That was all well and good, but it also meant that there was this thing out in space that we just had to learn more about. Thus, scientists from all over the world set to work. Known by the designation Cygnus X1, this black hole is situated in the constellation Cygnus, some 6,000 light-years away from Earth. It was a significant finding since it has a tremendous gravitational attraction and is around 14 times brighter than the Sun. Nothing can escape the gravitational attraction, not even light. This explains the name black hole. The idea of a black hole is equally unsettling and exciting. Nothing can escape from this area of space due to the intense gravity, not even light. Anything that approaches a black hole too closely will be drawn in and swallowed up, never to be seen again. However, the fact that they are dangerous makes learning everything there is to know about them much more important. Were we just getting started, or was this it? That turned out to be the correct response. Following the discovery of Cygnus X1, researchers began looking for more black holes. They discovered that the number of black holes in the Milky Way alone may be close to 100 million, but we still don't know for sure because they are so difficult to find. However, it appears that there are millions of black holes in our galaxy, the Milky Way, which increases the significance of studying them. So let's dissect it. Gravity will always be the primary issue with black holes. Anything that enters them will compress down astronomically until it becomes a singularity because to their strong gravitational attraction. Said another way, black holes may be thought of as cosmic vacuum cleaners that absorb everything. The idea that if a person were to fall into a black hole, their body would be stretched to the point of becoming a single line is among the most terrifying aspects of the study done on them. The patient would pass away before the final shape really took hold, and this process would be gradual. To put it simply, nobody ought to be entering one. But may we truly be in danger? They're everywhere? The nearest black hole to Earth is 1,500 light-years distant, yet that's still close enough to raise worries and questions. The first undistorted image of a black hole, the M87 black hole, was made public by scientists in 2021. The researchers took many nights' worth of pictures of this black hole, and with each one, they learned more and more about it. To construct something that filled in all the gaps, they had to stitch together the separate photographs. They were able to determine that a black hole had 3 levels in this manner. Contrary to popular belief, there is more than simply one massive void in the middle. That is not even close to how difficult things are. You have to pass through the first 2 levels of a black hole in order to even reach the empty space. The point of no return is found in the first stratum, which is referred to as the event horizon. There is no going back once you cross the event horizon, you will be drawn into the black hole. From that point on, it just gets worse. The area where light orbits the black hole is known as the photon sphere, and it makes up the second layer. The black hole's gravitational force will imprison any light that enters this area and prevent it from leaving. Ultimately, we reach the singularity, the third layer. Everything that enters the black hole is squeezed to an astronomical degree until it turns into a singularity at this point. The singularity is a moment in spacetime where the known rules of physics collapse and the future becomes unpredictable. The density is unlimited and the laws of physics as they exist today vanish at the singularity. Now, the worst part of all of this is that each black hole you investigate will be completely unique from the others. Although they often operate according to the same three-layer model, they may not work exactly the same manner. Now, if this were anything else, we could just get back on those telescopes and really examine the issue at hand. But it's not really possible to do that with black holes. Only by examining the radiation that black holes release and the gas and particles that surround them can scientists learn about them indirectly. Because everything that penetrates the event horizon is drawn towards the singularity, or it is compressed to an endlessly small point, sending a probe like the Voyager inside a black hole is not feasible. Therefore, it is not really feasible to squander billions of dollars in order to catch a glimpse every time, as the probe will just smash into oblivion as soon as it is close enough. Despite the fact that these items are actually three-dimensional phenomena, scientists are forced to investigate them in 2 dimensions due to this obvious issue. The fact that each black hole is different and that our understanding of the rules of physics is disrupted when we attempt to investigate the inside complicate matters further. This implies that the study of black holes cannot be adequately approached using the conventional scientific research methodologies. That is not to say that scientists haven't been working hard. Black holes are the subject of several ideas and explanations, and as time goes on, the complexity of the theories grows. The idea that collapsing stars constitute the source of black holes is among the most convincing explanations for how they arise. A star can no longer generate enough energy to fend against the relentless inward pull of gravity when it has used up all of its fuel. The star thus starts to collapse in on itself, getting denser and smaller as it does so. This process can go on until the star produces a singularity if it is large enough. NASA scientists focused on the center of the galaxy M87 in order to gain a deeper understanding of the nature of black holes. A violent vortex of extremely hot hydrogen gas was seen by astronomers whirling at an incredible speed of 1.2 million miles per hour. This rotating disk of gas should have violently broken apart in all directions due to its tremendous force, yet it didn't. To stop this from occurring, scientists reasoned that a massive mass centered in the galaxy's center was necessary. There was no way this enormous object, which weighed between 2 and 3 billion suns, wasn't a black hole. However, that is not the exclusive theory. Even black holes spin. In 1963, the most accurate description of a spinning black hole was given by New Zealand mathematician Roy Kerr using Einstein's equations of gravity. Kerr demonstrated that, contrary to what was previously believed, a spinning black hole will collapse into a narrow disk or ring of fire rather than a point. Because of the fast spinning, centrifugal forces would prevent the disk from collapsing. The region around the black hole is known as the ergosphere, and it is this spinning disk of matter that the laws of physics begin to break down. The fact that Kerr's solution anticipated the possibility of an Einstein-Rosen bridge, or wormhole, was its most exciting aspect, though. This is a hypothetical spacetime bridge that joins 2 distinct cosmological regions, or maybe 2 parallel worlds. According to the theory, if someone were to fall into a black hole, they would be launched out of a white hole in a parallel world and pulled down a tunnel through the ring of fire rather than being crushed to nothingness. We must examine Einstein's theory's idea of spacetime in order to comprehend how this operates. Spacetime is a 4-dimensional fabric made up of interrelated space and time, not 2 distinct things. Masses of things make this fabric to stretch, generating a gravitational field that draws other items toward them. Now picture spacetime on a piece of paper. The movement of things across spacetime can be illustrated by drawing a line connecting 2 spots on paper. However, what if you could make a shortcut between the 2 sites by folding the paper in half? This is a wormhole's fundamental concept. It's an instantaneous spacetime shortcut that links 2 far-off locations. Not only are wormholes a science fiction idea, but they are also a general relativity prediction. The reason wormholes collapse so quickly is because they are intrinsically unstable, even though no one has ever personally witnessed one. However, if an Einstein-Rosen bridge is real, then black holes might be more than simply cosmic vacuum cleaners, they might also be doors leading to different parts of spacetime. So is it possible for humans to travel through time and space using wormholes? Regretfully, the likelihood is probably not, at least not yet. It's doubtful that we could utilize a wormhole to travel faster than light, even if we could stabilize one. According to Einstein's special theory of relativity, there is an absolute maximum speed at which anything can move across spacetime, the speed of light. Perhaps still, scientists have been fascinated and intrigued by the idea that wormholes and black holes may be portals to alternate universes or perhaps to past eras for many years. The hypothesis that spacetime has shortcuts that enable travel across enormous distances or even into the past has the potential to be revolutionary. One of the most fascinating ideas in this field of research, if it could be realized, is the Kerr wormhole, so named for the mathematician Roy Kerr, who was the first to explain it using Einstein's gravity equations. This kind of wormhole is essentially a theoretical spacetime tunnel that might link two far locations, such two universes or even two distinct moments inside one world. Many people see the Kerr wormhole as a ring-shaped opening, much to the looking glass from Alice in Wonderland. Alice was sent to a realm where logic wasn't always applicable and animals talked in riddles as she passed through the looking glass. It is possible that traveling via the Kerr ring may carry a visitor to another world or era where the rules of physics are radically different from what we know. That may just be typical for the destination. As we've already touched on, wormholes as a potential route of time travel or intergalactic travel are an intriguing concept, but they're also a source of disagreement and discussion among physicists. Some have noted that because of the strong radiation and subatomic pressures at their entry, wormholes, especially Kerr wormholes, might be unstable or unfeasible to travel through. The detractors contend that the quantum forces governing radiation and subatomic particles are not affected by Einstein's equations of gravity, which are used to explain wormholes and black holes. A new theory that unites the laws of gravity with a quantum theory of radiation is required to fully comprehend the nature of these events. This is referred to as a theory of everything in the scientific community, since it is a single theory that can combine the quantum theory with Einstein's theory of gravity. Renowned theoretical physicist Michio Kaku has also spent decades developing a theory of everything. Although there are many possible interpretations of this, superstring theory is the only one that has demonstrated potential. Radiation theory and gravity are combined in superstring theory. According to the hypothesis, the cosmos is a symphony of tiny vibrating strings, which are actually subatomic particles. Various particles in nature correlate to various vibrations of a superstring, much as different musical notes correspond to different vibrations of a violin string. The idea that a string may create black holes, wormholes, and other unusual solutions to Einstein's equations by warping the space surrounding it as it moves through time is one of the most intriguing aspects of superstring theory. This indicates that superstring theory explains many of the enigmatic events we witness in the cosmos, in addition to tying Einstein's theory of gravity and the quantum theory together. But there's something about this hypothesis that, despite how straightforward it may seem at first, also makes more sense in a way. 10 dimensions of spacetime are needed for the strings to be able to vibrate according to superstring theory. Compared to the 3 dimensions of space and 1 dimension of time we encounter on a daily basis, this is completely different. Though it's hard to picture what these additional dimensions would be like, scientists have created several conceptual models that provide light on the matter. Think imagining a 2-dimensional pond full with fish that only know how big it is and how wide it is. These fish have no concept of height and have no idea what it would be like to exist in a 3-dimensional environment. The fish may perceive the impacts of the 3rd dimension even if they are unable to directly feel it, such as when rain falls on the pond and creates ripples. In a similar vein, physicists think that although we are unable to directly view the additional dimensions of spacetime, we are able to see their influence on the reality we live in. Specifically, in superstring theory, the vibrations of the strings can generate energy waves that pass through the additional dimensions of spacetime. These waves have the ability to take the form of particles with various characteristics, including mass and charge. Thus, all of the particles and forces that we can perceive in the cosmos, including gravity, may be explained by superstring theory. There's a catch, though. We are not really able to explore the additional dimensions of spacetime required by superstring theory directly because they are so tiny. The 4 dimensions of spacetime that we are familiar with, length, breadth, depth, and time, are the only ones that allow us to perform the most accurate measurements in our labs. How therefore can we even be certain that the other dimensions are real? One theory is that the extra dimensions are unseen to us because they are coiled up so tightly. Picture a tightly wrapped up piece of paper, like a cylinder. You might not even notice that the paper is curved if you were an ant moving over its surface. In the same way, the additional dimensions of spacetime and superstring theory may coil into microscopic spirals or loops that defy our perception yet influence the behavior of the vibrating strings within them. Another idea is that during the Big Bang at the beginning of the cosmos, the additional dimensions were more visible. Some interpretations of superstring theory claim that the cosmos was once a 10-dimensional spacetime with equally observable dimensions. The additional dimensions started to collapse and coil up as the cosmos cooled and expanded, leaving us with the 4 dimensions that we can see today. If this is the case, then there may be signs of the other dimensions in our environment. The superstring theory involves extremely complicated mathematics. It has made hitherto uncharted territory in mathematics completely accessible. On the other hand, the problem of a quantum black hole has proven to be difficult to solve. Despite several attempts by physicists, no one has been successful in solving this issue to far. Superstring theory has been described as 21st century physics that fell accidentally into the 20th century by Edward Witten of the Princeton Institute for Advanced Study. A major advance in physics was separately disclosed by multiple organizations last year. They discovered that the problem of a quantum black hole might be fully resolved by string theory, but only in 2 dimensions, not 10. Many physicists think that since the related equations are well defined while being challenging to solve, it's only a matter of time until someone solves this puzzle. Until then, at least when it comes to black holes, it's still too early to purchase tickets for interstellar or time-traveling excursions. One thing is evident from all of this: there are just too many questions and answers to these issues. Michio Kaku has shown how it is possible to determine the true nature of the answers to all of the wild notions. It's crucial to remember that string theory is not the only field in which the issue of endless replies arises, he added. In actuality, there are countless ways to solve a lot of brilliant hypotheses. Newton's rules, for instance, may be used to forecast the motion of a variety of items, including boulders and rocket ships, but first you must identify the object you are attempting to describe. We refer to these requirements as beginning conditions. In the same way, you have to explain to string theory what it is meant to describe. However, the Big Bang itself serves as the beginning condition for string theory, in contrast to other theories. This implies that you have to define the currently unknown conditions of the Big Bang at the moment of its creation. There are 2 methods to tackle this issue. One option is to use string theory to explain how the cosmos evolved after the Big Bang and conduct experiments to determine the original conditions at that point. Based on certain plausible estimations of its nature, string theory already has answers that explain the evolution of our universe since the Big Bang. This is a noteworthy accomplishment. Demanding that string theory choose its own beginning circumstances is an alternative and more ambitious course of action. That one is also less likely and a little more complex. Thus, we've already made a tremendous amount of progress. But Michio Kaku gives it all a different twist here. It's possible that the Big Bang wasn't as massive as first thought. He argues that contrary to popular belief, there wasn't a huge explosion. Furthermore, it didn't create the thunderous noise that one would anticipate from a bang. The Big Bang theory just asserts that there was a bang. It offers no explanation for what produced it or how it happened. In actuality, we require a hypothesis that explains the events leading up to the Big Bang. String theory enters the picture here. This idea suggests that our world may have evolved from the collision of 2 distinct universes, or that it may have originated from another universe, much like a child emerging from its mother. Wormholes are connections between worlds that resemble tubes joining 2 bubbles. There exists a possibility that we have already found proof of this umbilical cord connecting our universe to another. We could, in a sense, have been unaware that we had been living within a black hole the entire time. Consider this: it's feasible that we are truly within a black hole, and the black holes we study are wormholes to these other dimensions because we can only perceive things in 4 dimensions. Do you think there could be truth to that theory? Have you ever questioned whether there is more to life than meets the eye or whether we are truly alone in the universe? What happens if the James Webb Telescope ultimately establishes our existence within a black hole? Come along as we learn more about this mind-blowing, earth-shattering announcement that will cause you to re-evaluate everything you believe to be true about the cosmos. In the first place, what are black holes? They're frighteningly real. Although you may have seen them in science fiction films, the actual world is even worse than imagined. Some scientists claim that they are just black holes in space, but the reality is far more nuanced. In reality, black holes are enormous volumes of stuff compressed into extremely tiny spaces. Imagine a star 10 times as big as the Sun, condensed into a spherical the size of Manhattan. Nothing can withstand the gravitational pull of space, not even light. Ever since they began to consider objects in space that were so vast and dense that they might trap light, scientists have been enthralled with black holes. General relativity, the theory put out by Einstein, anticipated the most well-known theories regarding black holes. Essentially, a small, dense core is left behind after a large star dies. Everything is overpowered by gravity if the mass of the core is greater than 3 times that of the Sun. When you think about it, it's a very interesting and enigmatic occurrence, but it's also a little unsettling. So how are these black holes found by scientists? These objects don't release any light, so you can't merely aim your telescope at them and take a picture. In actuality, it is rather difficult to find black holes. However, scientists have discovered a means to make educated guesses about their existence by analyzing how they affect other adjacent matter. It all comes down to being aware of the cues. For example, accretion is the process by which a black hole draws matter to it from an interstellar cloud it passes through. But that's only the start. It's game over if a regular star gets too close to a black hole. As the material is drawn into the black hole, it can rip that star apart and release X-rays into space as it speeds and heats up. That's how indirect detection of black hole occurrence is possible for scientists. The most shocking thing, though, is that black holes drastically affect the communities that surround them. They have the ability to eat neighboring stars, release strong gamma-ray bursts, and even accelerate or halt the formation of new stars in specific regions. It's an enigmatic and startling occurrence that will definitely give you the chills. And from whence do they originate? Imagine this: stars that were once bright and brilliant finally explode in a stunning show known as a supernova. The fabled black hole, a mystery object, erupts from the remains of these fallen titans. Now, don't be misled by their name. These heavenly mysteries are not your typical holes. They eat everything that dares to approach them, much like the universe's version of vacuum cleaners. And you know what is really unsettling? Massive stars that have had a supernova explosion as their celestial retirement party give birth to the majority of black holes. It's as though their bright existence is coming to an end, leaving a gulf of unending blackness in its wake. The death state of smaller stars is known as neutron star transformation. Although they are extremely thick, light cannot be trapped by them. But if a star is a heavyweight champion, with a mass around 3 times that of our little Sun, then an astounding prospect emerges. It has been demonstrated by theoretical experts that there is no force in the universe that can stop this star from collapsing due to its own gravitational attraction. What a devastating fate that would be. Strange things begin to happen when this powerful star collapses. The star's surface approaches the event horizon, an unseen line, increasingly. This is when things start to become quite psychedelic. Time begins to deceive itself. When viewed from a distance, the event horizon appears to be where time slows down. Time seems to stop at that point when the surface contacts the event horizon, causing the star to collapse. It is as though the star's own clock runs faster than ours. Like an implosion that has frozen. Time frozen, quite eerie, don't you think? But well, what do you know? This story has an even more eerie twist. In the cosmic mosh pit, smaller black holes can occasionally collide and merge to become larger, more terrifying black holes. And just when you thought it could not get much uglier, consider the combination of a neutron star and a black hole. Their lethal dance creates an enormous nightmare, a horrifying thing beyond description. For years, scientists have had difficulty comprehending the magnitude of their own sizes. They seem to be the subject of a dark mystery that we are unable to solve. The truth is that there are two types of black holes, massive and little. The problem is that little is a relative concept. Relics from big stars, known as stellar mass black holes, can have a mass of up to 24 times that of the Sun. In the Milky Way alone, there may be between 10 million and a billion of them. There are an enormous number of black holes there, capable of consuming anything in their path. But there's still more. On the opposite extreme, supermassive black holes are millions or even billions of times bigger than the Sun. They are found at the core of massive galaxies, like the Milky Way. It's like a huge, black emptiness that is drawing everything in its direction. During his lifetime, famed scientist Stephen Hawking gave talks about black holes. Although the technology he needed to test some of his notions was lacking, his lectures were usually fascinating. But there is cause for optimism. Everything is changing due to a single scientific tool, and we are not prepared for it. It's here to explore the depths of our cosmos and goes by the name of the James Webb Space Telescope, or James Webb. We want to be clear, the James Webb is not your typical telescope. It's an engineering masterpiece that shows what the human spirit is capable of. Yes, we have launched other space telescopes in the past, and they have performed flawlessly. However, this bad guy is unmatched. The Hubble, which has faithfully served us for years, appears to be a small dot in the universe in comparison to the James Webb. And this cosmic marvel costs an astounding $10 billion. That's correct, there are enough zeros there to make your head spin. And get this, in addition to the priceless advice from more than 300 universities, the joint efforts of NASA, the European Space Agency, and the Canadian Space Agency were required to bring this miracle to reality. However, we must not overlook the dangers associated with such a large-scale project. This is definitely not a project for the weak of heart. The James Webb is exploring new ground, going beyond our current understanding, and visiting destinations we could only imagine. NASA recently revealed that the telescope has enough fuel to live more than double its minimum mission life expectancy of 10 years, following a successful launch. Numerous amazing accomplishments have been accomplished by the James Webb since its debut. It took it more than 1 million miles to get to its permanent home in orbit around the Sun. The telescope's enormous 5-layer sunscreen and enormous primary mirror, which had to be folded in order to fit on board the launch vehicle, were successfully unfurled during the voyage. Now that NASA has calibrated and adjusted it, the telescope is nearly prepared for full operation. The announcement by NASA that the James Webb Space Telescope had taken its first pictures of starlight was one of the most thrilling aspects of the telescope. The telescope's initial picture was of a star known as HD 84406, which produced a mosaic of 18 evenly spaced, brilliant spots from the star's light that were caught by the 18 mirror segments on the primary mirror. Afterwards, NASA unveiled an enhanced and refined picture of HD 84406, whereby 18 unfocused replicas of the star were consciously arranged in a hexagonal pattern. The observatory will start the image stacking procedure when it has correctly aligned each of the primary mirror's individual segments. This will stack 18 photos atop one another to create a single, crisp picture. The James Webb's advanced equipment will aid scientists in their exploration of the early phases of the cosmos following the Big Bang. It will investigate the events that took place during the epoch of reionization, which came about after the first stars created. This epoch describes the time when radiation from these early stars reionized neutral hydrogen, giving it an electric charge once more. Looking back billions of years is required for this, and a powerful telescope like the James Webb is the only tool that can do this. The telescope will also aid in the discovery of exoplanets, which are extremely hard to find due to their interactions with their host stars. Its potent sensors will be able to do more in-depth observations of these planets, which may include photographing their atmospheres in certain situations. Scientists may be able to more accurately forecast whether or not a planet is livable by having a better understanding of the planet's creation circumstances and atmospheres. In addition to examining how galaxies form, astronomers investigate galaxies to see the massive scale organization of matter. Thus, we are able to see the evolution of the cosmos. Over billions of years, the spiral and elliptical galaxies that we observe today changed from other forms. Examining the oldest galaxies to get a deeper understanding of their development is one of James Webb's objectives. Along with attempting to understand how we came to see the diversity of galaxies that we do, scientists are also attempting to understand how these galaxies now develop and assemble. Above all, though, the James Webb Space Telescope will enable us to address the most fundamental of questions: are we alone in the cosmos, or are we within a black hole? Additionally, James Webb has already begun searching. And you can probably guess what it discovered. 3 active galaxies have substances known as polycyclic aromatic hydrocarbons, PAHs, circling those huge supermassive black holes. These ring-shaped molecules made of carbon, known as PAHs, are the punk rock stars of the cosmos. From far-off galaxies to comets in our solar system, they may be found everywhere. Now, they're interesting not just because they could contain the elements needed to start life, but also because they aid in the tracking of star formation by astronomers. These PAHs become flamboyant and release infrared light when exposed to UV light. The mid-infrared instrument, MIRI, on board the James Webb can detect it, and typically that indicates the presence of some hot young stars nearby. Await the story twist, though. Ismael Garcia Burnett, our daring Oxford University astronomer, made the brave decision to look at 3 active galaxies, NGC 6552, NGC 7319, the eerily renowned Stephan's Quintet, and NGC 7469. These galaxies lie deep in the darkness, millions of light-years distant. The discovery Garcia Burnett made will cause your hair to stand on end right now. PAHs were abundant in the center regions where black holes rule supremely, according to MIRI. It sounds wonderful, doesn't it? The alarming part is that the radiation from those supermassive black holes warped the fundamental makeup of the PAHs. They became larger, more impartial versions of themselves as a result of it. The smaller, positively charged PAHs disappeared into thin air. Imagine being engulfed by the very blackness. There is, however, a ray of optimism. The reason the bigger PAHs survived is that they took refuge in gas-filled, thin, thick clouds. It's as though they have discovered their own shield from the dread of the black hole's fury. You may be wondering why this gloomy turn of events is relevant. Well, you see, astronomers who use PAHs to monitor star formation are faced with a bit of a dilemma. Electrically charged PAHs seem to be concentrated in star-forming areas. Tracking the birthplace of those stars becomes extremely difficult if the molecules are destroyed close to the black hole centers. But don't worry, our courageous astronomers aren't going to back down. Garcia Burnett intends to explore this dark cosmic chasm even farther with the group. The goal is to understand the mysteries of how these resilient PAHs manage to live in such terrible environments by analyzing additional active galaxies, each with a unique twist. They are looking at the unique characteristics of PAHs that may be hiding in the centers of galaxies that are home to black holes. This information is essential to comprehending star formation and the long-term evolution of these unsettling galaxies. The James Webb Space Telescope has revealed another astounding finding, though. Prepare yourselves for some really unsettling news. James Webb has discovered what may be the universe's earliest black hole. This celestial beast is a supermassive black hole, 10 million times heavier than the Sun. By examining tiny flashes of light that stretch back to the beginning of time itself, the James Webb was able to identify it. Situated at the center of a young galaxy, 570 million years after the universe's formation, lies this sinister and foreboding discovery. And here's the thing, astronomers think that much older black holes could exist elsewhere in space. Thinking about what more horrors could be out there, just waiting to be found, is both fascinating and horrifying. Undoubtedly, the James Webb Space Telescope is providing us with an unprecedented window into the deepest recesses of the cosmos, and the discoveries we're making are nothing short of astounding. The scientific community has been rocked by the finding of the universe's earliest black hole. This cosmic monster could just be one of several black holes that existed during the cosmic dawn, when the universe was just a billion years old and began to exist about 100 million years after the Big Bang. The sheer quantity of these black holes and their incredible growth leave astronomers perplexed. Despite publishing their results on the preprint website AR14, the researchers who made the most recent black hole discovery have not yet had their work peer-reviewed. Astrophysicist Rebecca Larson of the University of Texas at Austin, the study's lead author, thinks there may be a large number of undiscovered black holes out there. She said that we are now able to study cosmic history in a way that was previously unattainable thanks to the James Webb Space Telescope, and she is eager to see what more we will find. As we've already covered, black holes form when gigantic stars collapse and expand by engulfing everything in their path, including stars, gas, dust, and even other black holes. However, some black holes get so ravenous that the matter whirling about them warms up to the point where they begin to generate light that can be seen by telescopes. We refer them these as AGNs, or active galactic nuclei. Quasars, supermassive black holes that are trillions of times more massive than the Sun and release light bursts trillions of times brighter than the brightest stars, are the most extreme AGN. In order to obtain a sight of these elusive black holes, brave astronomers utilized the mid-infrared instrument, MIRI, and the near-infrared camera, NIRCam, two incredible infrared cameras. Equipped with these formidable weapons, they set out on a galactic expedition, surveying the heavens in pursuit of heavenly mysteries. It was more complicated than merely taking images, though. They had to solve the enigmas that were disguised by the light. That's where the integrated spectrographs in the cameras came in handy. They carefully dissected the light into its constituent frequencies like seasoned investigators, uncovering a wealth of data. Between the dim twinklings of the early cosmos, there was an unanticipated peak in the light's frequency spectrum. It resembled a warning sign that may indicate the existence of a black hole. They shivered as they realized that radiation was being emitted by the black hole's immense heat, faintly extending over the great expanse of space. The real mystery, however, was still how these black holes formed in the early stages of the cosmos so quickly. These astronomers' dreams were plagued by this question. They battled to find younger, hypothetical primordial black holes that may have formed immediately after, or possibly even before, the enormous explosion known as the Big Bang. However, despite their best efforts, these primordial black holes continued to be frustratingly elusive. How did black holes form and how did their incredible pace of expansion occur? Two dominant ideas with their own mysteries and shortcomings came to light. The first postulated that these black holes were the remains of huge stars, much larger than those that exist today. These extinct star giants would have developed at a speed that is incomprehensible to us, with a cosmic ballet between their birth and death. Although it was an enticing potential, time appeared to be the deciding issue. Because the cosmos was young, there had not been enough time for such a rapid process to take place. The second idea was as eerie but depicted the cosmos in a different way. It proposed that black holes, insatiable singularities of spacetime, were created when thick clouds of gas, towering like ominous specters, abruptly collapsed upon themselves. Although less plausible, this direct collapse scenario made sense given the quick creation, which called for a sizable volume of matter to fall straight into the center of darkness. The only limitation was time, as it always was, though it didn't seem like it in the early world. Another fascinating option surfaced when the researchers dug further into the vastness of knowledge. It had to do with the elusive population 3 stars, a legendary group of stars said to be the first in the universe. These stars, which are made entirely of hydrogen and helium, erupted early in the history of the universe. It was speculated that one such star had a catastrophic end, bursting in a dazzling display of cosmic fireworks. It left behind a black hole that was rabid, a cosmic devourer that was hiding in the shadows. However, this black hole was ravenous for evil. It grew at an extraordinary rate, dangerously consuming large amounts of surrounding stuff. It eagerly grew beyond expectations, defying stability. The researchers were perplexed by this peculiar behavior, which led to further inquiries regarding the cosmic forces at work. Unfazed by the cosmic mysteries around them, the researchers teamed up with MIRI's creators to form a potent coalition in their quest for solutions. Together, they set out on a brand new expedition to search for a stronger signal of the elusive light among those emissions by searching far-off galaxies. They weren't satisfied with merely catching glances. Their goal was to unearth well-kept mysteries, a mysterious code that would solve the mystery of the black hole that sat in the heart of the old galaxy. We have no idea what is in wait for us to uncover in the vastness of the cosmos. But the James Webb Space Telescope, our jaw-dropping telescope, is not done exploring yet. The top cosmic investigator has made an astounding discovery. And Here's the kicker: it has found not one, not two, but an astounding 6 massive old galaxies that have been dubbed universe breakers. Because they contradict all we now understand about the universe and have the potential to completely upend accepted cosmological ideas. Imagine that these magnificent galaxies are remnants of a time when the cosmos was only 3% of what it is now. The shocking thing is that they are quite large. We are discussing galaxies so massive that they dwarf the Milky Way, which is our own galaxy, in size. At a point in the cosmic chronology when scientists were expected to find little more than pint-sized infant galaxies, these universe breakers are strutting their stuff. But wait, these galaxies aren't just cosmic toddlers, they're fully grown adults living in a celestial playground. So how did these celestial giants come to be discovered by the James Webb Telescope? It combed through the old light released by stars and galaxies with its astounding infrared sensor equipment. You know what grabbed their interest, though? A bewildering deep red light emanating from a collection of hazy, blazingly brilliant specks. In the untamed field of astronomy, redness is an age indicator. The cosmos is expanding, stretching and redshifting light as it travels through it. You'll be shocked to learn how old these galaxies were. They emerged only 500 to 700 million years after the Big Bang, giving them an astounding age of 13.5 billion years. Even while the oldest galaxies previously seen by the James Webb Telescope were spectacular, at 350 million years old, they had nothing on these enormous cosmic children. The immense bulk of the recently discovered universe breakers made them look insignificant. These mind-bending galaxies have mass equivalent to tens to hundreds of billions of sun-sized stars. They are truly a match for the Milky Way, akin to celestial superstars. All of our preconceived notions about how galaxies form are called into question by the presence of these cosmic monsters. It seriously tampers with the foundations of our existing cosmological theories. It makes us re-evaluate the basic tenets of our theory on the formation of the earliest galaxies. Is it necessary to discard the cosmological rules or revise our theories on the formation of such young galaxies from small star and dust clouds? Imagine if the cosmos was meant to cool down slowly over hundreds of millions of years following a period of tremendous expansion, enabling gas to come together and create the first stars and galaxies. But wait, these massive galaxies imply that the gloomy ages, the period of time thought to have been a cosmic nap, might not have been as gloomy as previously thought. The cosmos appears to have punched the cosmic snooze button, causing star creation to explode into an incredible fireworks show much sooner than we could have ever predicted. Of course, further proof is required to properly validate this astounding discovery. The daring group of scientists behind this cosmic bombshell want to collect further data. Their goal is to obtain spectrum photos that will allow them to calculate the mass and precise distance of these extinct giants. Then and only then will we be able to determine if these universe breakers are genuine or whether we have discovered something much more astounding. However, if this wild discovery proves to be accurate, it will rock the scientific establishment and completely alter cosmology textbooks. In addition to the incomprehensible, who knows what other mind-bending cosmic shocks lie in wait for us in the vastness of space? The James Webb Space Telescope is on a quest to discover. We are getting closer to discovering the shocking and sinister truths hidden within the cosmos, which is full of riddles just waiting to be solved with every new finding. To discover the mysteries of the cosmos, physicists have historically relied on a variety of theories, including the Standard Model, quantum mechanics, and general relativity. These theories have been successful in providing an explanation for cosmic occurrences, illuminating the behavior of celestial bodies and the complex nature of particles at the tiniest scales. There would be a plethora of unresolved questions about the universe if theories weren't there to guide us. But what if all along we've been mistaken? At last, Brian Greene has come out to say that we are living within a black hole and that all current hypotheses are false. Come along as we unravel the mystery of what Brian Greene was discussing 0.4 billion years ago, rotating around each other, approaching the speed of light, colliding, and causing a tidal wave in the fabric of space, and consider how this finding might alter everything we have ever believed to be true about our reality. Few voices are as influential in the field of theoretical physics as Brian Greene's. His outstanding contributions to the subject, especially in the area of string theory, are irrefutable. He has become a significant figure in the scientific community due to his breadth of knowledge, coherence of ideas, and ability to explain complex ideas to both specialists and lay people. Greene's knowledge goes much beyond his outstanding findings in study. He has a remarkable gift for using his writings, talks, and media appearances to help solve the universe's puzzles. He has succeeded in bridging the gap between the curious public and the arcane realm of theoretical physics with his best-selling books like The Elegant Universe and The Fabric of the Cosmos. His exceptional talent at reducing intricate concepts to universally understandable stories has enabled a great number of individuals to interact with difficult scientific topics. Thus, he has also contributed to the expansion of the scientific community at large. However, Greene's professional achievements and educational background are what really establish his powerful standing. As a physics and mathematics professor at Columbia University, he has fostered a new generation of scientific minds by mentoring and inspiring many young scientists. His work in string theory, a framework that seeks to unite the fundamental forces of existence, has advanced the discipline and brought him international acclaim from peers and specialists. Therefore, the world pays attention to what a man like him says. Furthermore, he has suddenly declared that every contemporary theory that we had previously relied upon for explanations is false. We live inside a black hole as opposed to merely our solar system. We have been within a black hole the entire time, and everything we have been taught about our world is untrue. However, how is it possible? Could contemporary theories be so incorrect? In fact, scientists have been investigating the possibility that our universe may be contained within a black hole for some time now. A number of hypotheses and concepts have been put out over time to explain how our universe could be related to or descended from black holes. Some scientists have proposed that every black hole has the capacity to create a new universe. This idea is based on the theory of torsion, which postulates that a new universe is produced inside every black hole. This view holds that black holes serve as cosmic portals via which new universes are born. According to a different theory, the black hole that houses our observable world is a component of a bigger parent universe, or multiverse. According to this perspective, black holes act as portals to different areas or dimensions of spacetime, which include several worlds or universes. It is also thought that the singularity, or the endlessly dense center of a black hole, might be the place where new universes are created. There are specialists who propose that our cosmos could have originated from the singularity inside each black hole. This theory makes a connection between black hole singularities and the original condition of our cosmos, which is known as a singularity. The idea that a black hole within another universe is the source of our cosmos is another intriguing possibility. This hypothesis states that a white hole on the opposite side of a hypothetical wormhole concurrently gives birth to a parallel universe when a black hole arises as a result of the collapse of a dying star. This theory links the genesis of new universes to the production of black holes. Not only that, but some theories even suggest that our universe may be within a black hole with a higher dimension. According to this viewpoint, our cosmos originated as a singularity, a point of infinite density and temperature, much to how black holes are described by science. According to the theory, a four-dimensional black hole's event horizon contains our universe. This would imply that, despite our best efforts, we are unable to detect the fact that we are within a black hole. However, as you can see, this hypothesis contradicts all of the facts we have already researched and established about how our own universe functions. From the greatest structures to the tiniest constituents, the basic essence of the world is sought to be explained by a variety of theories within modern physics. These ideas, which have been created by thorough scientific research, have offered amazing insights into how the universe functions. The foundation of quantum mechanics, which explains how particles behave at the atomic and subatomic sizes, is the basis of contemporary physics. It presented an alternative path from the rigid principles and exact measurements of classical physics. Wave-particle duality is a fundamental idea in quantum physics that reveals the nature of the microscopic universe. It demonstrates how particles like electrons and photons may have characteristics of both waves and particles. This implies that in addition to exhibiting wave-like properties like interference and diffraction patterns, they may also behave as discrete particles with precisely defined locations and momenta. The mathematical description of quantum mechanics, which describes the probability distribution of finding a particle in various states using wave functions, captures this duality. Superposition is yet another amazing feature of quantum physics. This concept asserts that particles can exist in more than one state at the same time, which is not seen in traditional physics. An electron, for instance, can exist in both spin-up and spin-down states simultaneously until a measurement is taken, which collapses the wave function into one of the conceivable states. Then there is entanglement, which is yet another fascinating aspect of quantum mechanics. When two or more particles exhibit strong correlation, their states become interdependent despite being separated by great distances. Regardless of the physical distance between two particles, when they are entangled, measuring the state of one particle instantaneously determines the state of the other. This phenomena is being investigated for potential uses in quantum computation and communication after being verified experimentally. The power of quantum mechanics to precisely anticipate and explain a wide range of tiny occurrences is what makes it so successful. It offers a coherent framework that can explain how photons are emitted and absorbed, how electrons behave within atoms, and how particles interact within particle accelerators. This knowledge has aided in the creation of several quantum mechanically based technologies, including transistors, lasers, and nuclear power. Upon closer examination, quantum mechanics provides a microscopic understanding of the world we live in. These are the building elements of existence, and we have understood that everything operates in a specific manner, the way that reality is meant to be, ever since their discovery. That's not all, though. Numerous theories have long been employed to explain the nature of our planet and the workings of the actual world. One such theory is general relativity, which defines gravity as the curvature of spacetime brought about by matter and energy. It offers a mathematical foundation for comprehending the actions of huge objects, such as galaxies, planets, and stars. Numerous phenomena, like as the expansion of the cosmos, the precession of Mercury's orbit, and gravitational lensing of light, are satisfactorily explained by the theory. Even yet, there are extreme situations where general relativity fails, including at the core of black holes or in the first moments of the Big Bang, necessitating the development of a more comprehensive theory of gravity. However, particle physics standard model goes one step farther. This is a very effective theory that offers a thorough framework for comprehending the underlying particles and forces that comprise the cosmos. It includes the weak nuclear force, the strong nuclear force, and the electromagnetic force, three of the four fundamental forces. Every one of these is essential to the operation of our cosmos. Interactions between charged particles, such electrons and protons, are caused by the electromagnetic force. Conversely, some nuclear reactions and radioactive decay are examples of processes that involve the weak nuclear force. Strong experimental evidence supporting the validity of the electroweak hypothesis has been supplied by the finding of the W and Z bosons, carriers of the weak force. Atomic nuclei are held together in the conventional model by the strong nuclear force. It is in charge of the interchange of gluons that occurs between quarks, the basic particles that comprise protons and neutrons, during their interactions. The strong force's behavior is described by quantum chromodynamics, a branch of the standard model that has undergone satisfactory experimental testing. Therefore, the theories we are discussing here are not just hypotheses, they are the reality, as evidenced by numerous instances of proof. Furthermore, the Higgs boson, a particle connected to the Higgs field, was also expected to exist under the standard model. It is believed that interactions between particles and the Higgs field are what give particles their mass. The Higgs boson's existence was verified in 2012 by experiments carried out at the Large Hadron Collider, adding even more support to the standard model. However, in spite of its achievements, the conventional model is not without flaws. Its inability to take into consideration the existence of dark matter and dark energy, which are thought to make up a sizable fraction of the universe, is one of its main limitations. It is deduced from dark matter's gravitational pull on visible matter that it is a kind of matter that is unaffected by light or other electromagnetic waves. On the other hand, the observed accelerated expansion of the cosmos is thought to be explained by dark energy. Comprehending the characteristics of dark matter and dark energy, which are essential components of black holes, is still a thriving field of scientific inquiry. But the difficulties don't end there. The attempt to integrate the gravitational force with the other basic forces presents another challenge. Gravity is not represented by the standard model, rather, it is described by the independent theory of general relativity. So perhaps Brian Greene is right after all. As you can see, his real area of specialty is investigating the essence of the cosmos, looking for a single theory that unifies all the forces and particles. Greene's work on the idea of mirror symmetry and superstring theory is one of his most important contributions. A deeper relationship between two seemingly different Calabi-Yau manifolds, higher dimensional geometrical spaces, is established by mirror symmetry. The surprising connections between what appeared to be disparate mathematical explanations of the cosmos were revealed by this finding, which completely changed our understanding of string theory. These little variations also allow for Greene's idea. Perhaps the distinctions, little as they may be, add up to something more than the realization that we are not alone in space. Perhaps all along we have been living within a black hole. But as you can see, things get much more fascinating at this point. The scientific community frequently discusses black holes for a reason. As more is discovered about this one topic, the mystery surrounding it only grows. As to prevailing beliefs, a black hole is an area in space where the gravitational pull is so powerful that nothing can escape it, not even light. This extraordinary property results from the extreme concentration of mass in a small region, which completely distorts space and time around it. The truth is that black holes have incredible characteristics that distinguish them from all other things in the cosmos. Their extreme density is one of their distinguishing characteristics. A black hole's mass is concentrated into a little area, creating a gravitational field with enormous strength. Since even particles traveling at the speed of light cannot overcome this gravitational pull, an event horizon, a limit beyond which nothing can return, forms. Black holes only have three characteristics, though, despite their enormous gravitational attraction: mass, spin, and electric charge. The main feature that distinguishes a black hole and ultimately determines its gravitational pull is mass. An object's spin, or its angular momentum, is what gives the black hole its name. These items rotate in an angular manner rather than in a clear-cut, uncomplicated manner. That explains why black holes can vary from one another as well. The entire black hole alters at even the smallest variations in their angular momentum. Although theoretical physicists have created a number of theories to explain many black hole varieties, stellar mass black holes are by far the most prevalent kind. They are the result of huge stars collapsing gravitationally at the conclusion of their life cycles. The mass of a stellar mass black hole usually varies from 3 to several hundred times that of our Sun. Their development is a result of a catastrophic event when a dying star's core collapses due to its own gravity, creating a compact object with a strong gravitational attraction. There are theoretically more kinds of black holes than stellar mass black holes, such as supermassive and primordial black holes. Most galaxies, including our own Milky Way, are thought to have supermassive black holes at their cores. Even though their mass is millions or even billions of times that of our Sun, scientists are still trying to figure out how exactly they formed. On the other hand, primordial black holes are speculative objects that could have developed soon after the Big Bang. Their mass might vary from microscopic to enormous, and they would have come from instabilities in the early cosmos. Though analyzing the more intricate black holes may be a little more challenging, scientists are nevertheless aggressively searching for and studying every black hole they can locate. Black holes may be found and studied using a range of techniques that astronomers use, which helps us understand more about these cosmic objects. One method is to measure the gravitational pull that black holes have on nearby stuff. The motion of stars and other bright objects provides astronomers with information on locations of extreme gravitational force. For example, stars have been discovered orbiting an apparently empty area at the heart of our Milky Way galaxy, which suggests the presence of a supermassive black hole. A further approach is to investigate stuff that is accreted into a black hole. An accretion disk, a structure made of gas and dust in the shape of a disk, is created when matter spirals into the black hole. Extreme heat is produced by the disk's friction and strong gravitational pull, which leads to the emission of X-rays and other wavelengths of light. This gives scientists important new information about the properties and actions of the black hole. Astronomers may even be able to see the dazzling emissions coming from matter falling into a black hole up close in certain instances. Matter travels at extraordinary speeds in the direction of the black hole, producing a great deal of heat and radiation. Scientists may analyze this radiation, which can be detected at many wavelengths ranging from visible light to X-rays, to get important insights into the characteristics and workings of black holes. However, this is not how all black hole research is done. Another way to find black holes is to observe how neighboring stars move. Astronomers can identify aberrant patterns or aberrations that indicate the existence of an incredibly large object by analyzing the exact motions of stars in the region of a suspected black hole. These findings improve our knowledge of the black hole's gravitational pull by offering important hints about its mass and position. An additional line of inquiry into black holes has been made possible by the discovery of gravitational waves. Massive objects accelerate and generate ripples in spacetime known as gravitational waves. Strong gravitational waves are released when two black holes merge, and these waves may be seen by specialist observatories such as the Laser Interferometer Gravitational Wave Observatory, LIGO. These discoveries give concrete proof of black hole collisions as well as important new information on the masses and distances of the involved objects. Over the last several decades, science has advanced significantly. In order to detect active black holes in a large number of galaxies, scientists have created novel algorithms in recent times. For example, Australian astronomers have modeled the radiation from galaxies and black holes at various wavelengths using an algorithm known as Prospect. They can now recognize the telltale signs of active black holes thanks to this approach, which also helps to explain their features and frequency in the cosmos. Scientists use a variety of techniques to investigate black holes in depth after they are discovered. They track the movement of gas and stars in the black hole's neighborhood to gain information about its mass and the gravitational pull it has on its surrounds. This contributes significantly to our understanding of the physical processes around black holes. Another method for studying black holes is reverberation mapping. By monitoring the temporal differences between emissions from several areas close to the black hole, this approach may be applied. Astronomers can decipher the mechanics of the accretion disk and the interaction between matter and radiation by examining these temporal delays, which allow them to sketch out the orbits of gas and photons around the black hole. That's not all, though. Additionally, state-of-the-art investigations like the Event Horizon Telescope, EHT, have completely changed our understanding of black holes. With the help of the EHT, a global network of radio telescopes, scientists can now take unprecedentedly high-resolution pictures of black holes. The EHT functions as a virtual telescope the size of Earth. The event horizon was visible thanks to the telescope network's successful imaging of the supermassive black hole at the galaxy's center, M87. It is one thing to be able to observe what scientists have been describing for decades, even though this was also known in the past. You would think that everything would be obvious now. That a black hole has been observed, right? However, it is where Greene undermines all of that reasoning. His provocative theory suggests that the cosmos we live in is contained by a black hole. In actuality, this assertion arises from the complex interactions between black hole physics, quantum mechanics, and general relativity. Greene argues that fascinating possibilities arise when we apply the principles of general relativity, in particular, Einstein's theory of gravity, to the enormous size of the universe. Due to their strong gravitational attraction, black holes can cause major distortions to space and time in their surrounding areas. The fabric of spacetime becomes very twisted inside the event horizon of a black hole, where gravitational forces are at their highest, producing some really intriguing phenomena. According to Greene, the structure and expansion that we can see in the universe would be caused by gravitational forces operating inside a black hole. In this case, stuff falling into the black hole from outer areas would exert a gravitational pull that would cause the universe to expand. A possible explanation for the formation of stars, galaxies, and other celestial formations that scientists have been researching for decades is the gravitational collapse of matter. In fact, Greene's theory presents some very interesting options for solving some of the enduring riddles in contemporary physics. The fundamental incompatibility of general relativity and quantum mechanics is one of them. Quantum physics controls the behavior of particles at the subatomic scale, whereas general relativity effectively explains the action of gravity on a cosmic scale. It has long been a difficulty to combine these two theories into a single framework, sometimes called a theory of quantum gravity. Greene believes that the theory that we live within a black hole may offer a suitable framework for combining quantum physics and general relativity. It's possible that the Enormous gravitational forces seen inside black holes might create a very special environment in which the fundamental principles of physics are altered. Furthermore, the idea of residing within a black hole may provide insight into the riddles of dark energy and dark matter. Even though these enigmatic elements comprise most of the matter and energy in the cosmos, little is known about them, including their nature and characteristics. Given that the characteristics and actions of the black hole itself may be responsible for the impacts of dark matter and dark energy on the cosmic scale, the idea that one is inside one might provide a possible explanation for their existence. However, if Greene's idea turns out to be true, it would completely re-evaluate the fundamental principles of physics and completely transform our present cosmological models. Although it is difficult to find direct observable data to confirm or deny this idea, there are some possible ways to assess its veracity. Finding observable signs that may distinguish between a world within a black hole and a cosmos that adheres to the conventional cosmological framework is one option. For example, some trends in the cosmic microwave background radiation, or remnant radiation from the early cosmos, may offer clues about the composition of the environment in our universe. An alternative strategy would be to do in-depth research into the behavior of particles at very high energy, such those generated in particle accelerators. Particles close to the intense gravitational forces within a black hole may behave in ways that are unique from what we now know about particle physics. Perhaps something is hiding in the details that we have been oblivious to all along. Thus, it would now be necessary to carry out theoretical studies using sophisticated mathematical models and simulations in order to investigate the effects of being within a black hole. These simulations may shed light on the physical rules, gravitational dynamics, and predicted observable signs that would be present in such an environment. If Greene's idea is indeed plausible, it might be verified by contrasting these predictions with observable evidence from astrophysical experiments or cosmological surveys. However, there are others who disagree with Brian Greene's theory, which contends that we live within a black hole, despite the fact that it is an exciting and thought-provoking idea. Several cosmologists and physicists present other viewpoints that completely refute Greene's theory. The concept of the multiverse provides one alternate perspective. According to the theory of the multiverse, there are many other worlds besides our own that exist. These realms are referred to as the multiverse. It's possible that every world in the multiverse has its own distinct set of physical constants, rules, and characteristics. This concept originates in several areas of theoretical physics, such as inflationary cosmology, quantum mechanics, and string theory. Proponents of the multiverse hypothesis contend that the presence of several worlds, each with unique attributes, might account for the wide range of physical laws and constants found in our universe. Basic factors including the intensity of gravity, the values of basic forces, particle masses, and even the number of dimensions might vary among these many worlds, sometimes known as pocket universes. According to this theory, the characteristics of our universe are only one conceivable arrangement among many that exist, neither exceptional nor unique. Maybe our world isn't the one within a black hole, but there could be other versions out there. The inflationary multiverse scenario, or endless inflation, is one specific multiverse idea. This theory states that the early universe had a phase of rapid expansion known as cosmic inflation, which produced new areas that eventually separated into universes with distinct physical characteristics. The speed of light. What prevents signals or information from traveling across these worlds, causing them to be causally separated from one another. One approach to answering the topic of how our universe is adjusted is through the multiverse hypothesis. The astounding accuracy of the underlying constants and physical rules that let life as we know it to exist is referred to as fine-tuning. Proponents of this hypothesis contend that if several universes exist, each with unique qualities, then it shouldn't come as a huge surprise if one of them has the ideal environment for life. According to this theory, the likelihood of discovering a world conducive to life is increased by the presence of a multiverse. However, you might also examine the complete opposite viewpoint. Perhaps the entire universe is a simulation. Over time, the hypothesis that our universe is a simulation of reality has drawn a lot of interest from philosophers and scientists alike. This theory holds that rather than being founded on physical rules and occurrences, our experience of reality, including our presence within a black hole, emerges from a virtual world constructed by highly evolved species or a higher intelligence. proponents of the idea of simulated reality contend that observed phenomena, including gravity and the universe's structure, may be computer-generated models intended to replicate the features and actions of a black hole. From this angle, rather than being a genuine physical occurrence, Greene's sense of being within a black hole may be the product of programming or constraints in the underlying simulation. The quick development of virtual reality and computer simulation technology is a major source of inspiration for this point of view. It is not so implausible to envisage more evolved civilizations or creatures capable of simulating entire universes, especially as our own technical skills to create realistic simulations and immersive virtual worlds grow. The simulation hypothesis is further supported by a number of theoretical and philosophical considerations. For example, the simulation thesis put forth by philosopher Nick Bostrom implies that if technologically advanced civilizations exist, they probably have the capacity to produce lifelike simulations of conscious entities. It is statistically more likely, so the reasoning goes, that we are living in a simulation than in the actual world. Furthermore, observational constraints exist. Direct proof or observations from within a black hole are very difficult to get due to the strong gravitational attraction of the event horizon. Additionally, because of their nature, black holes are impervious to signals or information, making it challenging to explore their interiors and confirm if a universe exists there. That's not all, though. In addition, the theory calls into question the characteristics of space within a black hole and the meaning of time. There are difficulties in comprehending how our universe, with its rules of physics and structure, could persist under such conditions due to the high gravitational forces and curvature of spacetime near the singularity. The concept of a self-contained world within a black hole is complicated by the effects of time dilation and spacetime distortion. For the moment, however, let's set all of that aside and consider the possibility that we genuinely live within a black hole and that everything you believe to be true about the universe is untrue. One issue would naturally come to mind in this situation: if we are indeed within black holes, then how have we managed to gather such extensive information about other black holes during this time? Actually, there are a number of really interesting theories here. According to one hypothesis, the border of an area of space can encode all the information about it. This theory is based on the holographic principle. In this scenario, the universe may be a higher dimensional depiction of physical processes taking place on the edge of a black hole, or it may be a holographic projection. This would enable humans to see and study other black holes in our universe while continuing to live inside the black hole. The brain world theory, which postulates that our universe is a four-dimensional brain buried within a higher dimensional spacetime called the bulk, is another intriguing concept. This hypothesis states that black holes can originate in the bulk and in our universe, which would be the brain. Even if we live inside a black hole on the brain, we are nevertheless able to see and learn about other black holes that are part of the bulk dimensions. In fact, there are hypotheses that suggest that human capacity to live within black holes and conduct research on other black holes may be related to the phenomena of quantum entanglement. A phenomenon known as quantum entanglement occurs when two or more particles interact in a way that causes their states to instantly correspond, regardless of their distance from one another. It is proposed that humans might be able to study and learn about other black holes indirectly if there is entanglement between particles within and outside of a black hole that stretches over the event horizon. Perhaps Greene isn't speaking of impossibilities after all. Perhaps he is the only one who perceives this as the true reality, that we are in fact within a black hole and all current explanations are false. Do you agree with him?
They said that the James Webb Space Telescope saw a big object moving toward Earth from about 10 light years away. The James Webb Space Telescope has opened up a new era of astronomical finding by giving us looks into the farthest reaches of the universe. Reports say that this cutting-edge camera has taken the first real picture of the inside of a black hole, showing that it is now much more powerful than ever before. Not only scientists, but also well-known people like Elon Musk and Michio Kaku have paid attention to this important event. This kind of finding is more than just interesting, it touches on the deepest puzzles of spacetime, matter, and the rules of physics. Before we start, click like and subscribe to get more exclusive stories. People used to think that black holes were the most mysterious and hard to find things in the universe. They are places in space where gravity is so strong that not even light can escape. They are made up of the remains of huge stars that fall apart due to their own gravity, leaving behind a singularity, a point with infinite density, and an event horizon, the edge beyond which nothing can return. Scientists have had ideas about what lies beyond the event horizon for many years. Mathematical models and computer simulations have shown that black holes might hold secrets about how spacetime and gravity work. We had only seen black holes indirectly up until now, by looking at how they affected nearby objects and the radiation they gave off from the rings of gas and dust as they shook. The Event Horizon Telescope, EHT, took a picture of the supermassive black hole at the center of the Messier 87 M87 galaxy in 2019. This picture was hailed as a great success. But the picture was actually a blurry, donut-shaped ring of light around a dark area in the middle. This was the event horizon's outline, not the inside of the black hole. With its unique infrared abilities, the James Webb Space Telescope is a huge step forward from what the EHT could do. The James Webb Space Telescope is about 1 million miles away from Earth and is meant to look deeper into the universe by picking up light from the oldest galaxies and showing features that have not been seen by other telescopes. The picture it took of the inside of a black hole is the first straight look beyond the event horizon in the history of science. Not only has this discovery caused a lot of joy, but it has also led to a lot of new questions about what reality is. Elon Musk, a tech billionaire and space entrepreneur, was quick to say how excited he was about the finding. Musk is known for his big plans for space travel through SpaceX. He has talked a lot about his interest in black holes and how they might help us understand the world. The importance of this finding fits with Musk's interest in the unknown and the limits of what scientists can know. He thought that the picture could give us information that would help us make technological advances and maybe even help us figure out how to fly to other planets in the future. Musk has always been hopeful about exploring beyond our solar system because he believes that learning about the universe's harshest places, like black holes, will eventually lead us to new discoveries. The famous theoretical physicist and futurist Michio Kaku also spoke about how important the James Webb discovery was. Kaku has long pushed for making physics more accessible to the public and for simple science ideas to be understood by everyone. He has talked a lot about the ways that black holes can help us find a way to combine all the rules of physics. His argument is that finding the inside of a black hole could help solve one of the biggest scientific mysteries of our time, the clash between general relativity and quantum physics. Einstein's theory of gravity, called general relativity, explains how heavy things bend spacetime and control the movements of everything around them, even light. While quantum physics, on the other hand, describes how particles behave at the smallest sizes. Both ideas have been proven to be true in their own areas, but they don't work together at all. With their strong gravity and very small singularities, black holes are the perfect place to test a unified theory, which is sometimes called the theory of everything. Kaku thinks that looking into the center of a black hole could show us the quantum structure of spacetime, which could help us understand the universe's most basic forces better. The James Webb Space Telescope took the first real picture of the inside of a black hole. This picture is expected to change many long-held beliefs about these huge cosmic objects. Over the years, scientists have thought that the inner event horizon, a place deeper inside the black hole where the known laws of physics might not apply, might exist. The picture taken by James Webb seems to prove that such a place exists, but it also adds to the complexity of the situation. Early studies show that the space inside the black hole might not be the smooth, empty void that many people thought it would be. Instead, it might be a very fluid place where quantum changes cause ripples in the very structure of spacetime. This finding is important for both theoretical physics and the study of astronomy as a whole. Black holes are thought to be very important in how galaxies form and change over time. Learning about the insides of galaxies, like our own Milky Way, could help us figure out how they formed. Also, black holes might hold information about what will happen to the world in the end. Some ideas say that black holes might finally disappear through a process called Hawking radiation, which is named after the famous physicist Stephen Hawking. If this is true, black holes might lose mass slowly over time until they disappear, leaving only radiation behind. The picture taken by the James Webb Space Telescope could help scientists test this idea and find out if black holes really do disappear or if they could live on forever in some way. This finding has effects that go even further into the world of theoretical science. Some experts think that black holes might be doors to other dimensions or worlds. This idea comes from the idea of a wormhole, which is a made-up tunnel through space-time that could join faraway places in the universe or even worlds that are not connected to each other. If these kinds of structures are inside black holes, they might be able to help us move across very long distances in space or even through time. At the moment, there is no proof to back up these claims, but the picture taken by James Webb could be the first real data that lets experts test these ideas. One of the most exciting things about this finding is that it makes new study possible. In the years to come, the James Webb Space Telescope will likely keep looking at black holes, improving its methods and getting even clearer pictures. Scientists will learn more about the strange forces at work inside these cosmic giants with each new observation. The information the James Webb Space Telescope gathered could also be used to help create new tools and devices that will allow us to look even deeper into the universe. Based on how well the James Webb Space Telescope worked, future space projects could use even more powerful cameras or send probes close to black holes to collect more data. This picture of the inside of a black hole also makes me think about the nature of reality itself. Black holes make us think about what space and time mean and push these ideas to their limits. Spacetime curves forever around the singularity at the center of a black hole. At this point, the rules of physics as we know them no longer apply. This makes me think that black holes might help us figure out what the world is really like beyond what our present theories can explain. The find makes many people think about how much we still don't know about the universe. Even though science has come a long way over the centuries, the world is still full of secrets. For example, no one knows what dark matter and dark energy are or if there is life on other planets. The picture that James Webb took of the inside of a black hole shows how curious and resourceful people are. It shows that with the right tools and persistence, even the hardest questions can be answered in the end. Scientists from many different fields work together on the James Webb Space Telescope. This shows how important it is to do study across disciplines in order to fully understand the world. Astronomers, engineers, mathematicians, and physicists have all worked on the James Webb Space Telescope and helped look at its data. Working together has not only helped us learn more about black holes, but it has also shown how powerful it is to push the limits of what we can do as a science community. One of the most important events in the history of modern science was when the first real picture of the inside of a black hole was taken. In a big way, it changes how we think about the world and gives us a look into a part of space that we used to think was totally out of reach. This accomplishment brings us closer than ever to solving the riddles that have long ringed black holes. It not only gives us a better understanding of these mysterious cosmic objects, but it also gives us a chance to look into the basic rules of nature in a way that has never been done before. One of the most important and direct effects of this finding is that it might help us learn more about the event horizon, which is the edge of a black hole beyond which nothing can escape. The James Webb Space Telescope took this picture. Before this picture was taken, black holes were mostly studied in other ways. Researchers could only guess about their features by looking at how things and light behaved near the event horizon. But this new picture gives us a clear picture of what's inside, giving us information that we couldn't have imagined before that could completely change how we think about the physics at work in these harsh settings. Matter and energy inside the event horizon are hit by gravity forces that are so strong that space and time don't work the way they should. The theory of general relativity, which has been the basis of our knowledge of gravity for more than 100 years, accurately predicts how black holes will behave, but it doesn't fully explain what happens inside these objects, especially in the singularity. The singularity is the point where there is no more mass and no longer any rules of physics that can be used. The James Webb Space Telescope took a picture of the inside of a black hole, which makes it possible to test these ideas in ways that weren't possible before. This important discovery could also have big effects on the study of quantum physics. Michio Kaku said that black holes are a unique way to look at how general relativity and quantum physics might be able to work together. For decades, scientists have been trying to figure out why these two important ideas in modern physics don't seem to go together. Quantum physics describes how subatomic particles behave, while general relativity describes how big things in space behave. Because black holes have singularities that are infinitely dense, they are right in the middle of these two sets of rules. This makes them perfect for trying a single theory of quantum gravity. In time, scientists may be able to use pictures of the inside of a black hole to find out about the quantum features of spacetime itself. Some theories say that spacetime is not a smooth continuum at very small sizes, but is made up of discrete quantum bits of energy. Quantum gravity is the study of how the fabric of spacetime might behave at the Planck scale, which is the smallest distance that matters in physics. This idea is at the heart of quantum gravity. If you look inside a black hole, you might see patterns or events that provide clear proof for this quantum structure. This could lead to answers to long-standing questions about how reality really works. One of the most important things this finding does is change the way we think about time. General relativity says that time is not a set and unchanging constant. Instead, it is a dimension that can grow and shrink based on the gravitational forces at work. Time slows down a lot for things close to the event horizon because black holes have so much force. This is called time dilation. Looking into the center of a black hole, where gravity is even stronger, might give us the most correct information we have yet on how time dilation works. This could help us learn more about how time flows in extreme situations, which could lead to a better understanding of how time, space, and gravity are connected. The find brings up the so-called information paradox again, along with the idea of time dilation. Stephen Hawking famously said in the 1970s that black holes might be able to give off radiation, now called Hawking radiation, that would finally evaporate and go away. But this radiation seemed to go against another well-known principle of physics: information stays the same. Quantum theory says that details about a system's first state should never be lost, even if the system changes or breaks down. But if black holes could fully disappear, it made me wonder what would happen to the data about the things that fall into them. Is it lost for good, or does it get away? The picture taken by the James Webb Space Telescope could help solve this puzzle by giving us new information about whether black holes really delete data or if it is kept safe in some unknown way. There are more fanciful ideas about the nature of reality that are based on the idea that black holes might store information. One such idea is that black holes could project data stored on their event horizons like holograms. Based on the hologram principle, which comes from string theory, this idea says that all the information inside an amount of space can be shown on the edges of that space. In this case, black holes might follow this rule, which could mean that their huge, complicated innards are like representations of the data stored on their event horizons. Taking a picture of the inside could help test these ideas. It would be the first real-world proof of the holographic principle and change the way we think about spacetime and information theory. This finding doesn't just have implications in the area of physics. People have long thought that black holes are very important to how galaxies change over time. People think that supermassive black holes, like the one at the center of our galaxy, Milky Way, can change how stars and other celestial objects form and behave on a cosmic scale. A picture of the inside of a black hole could tell us a lot about how these very large things interact with the world around them. It might show how black holes take in matter, how they send out powerful energy jets, and how they change the structure and motion of galaxies as a whole. In addition, black holes may help us figure out some of the most puzzling things in the world, like dark matter and dark energy. One of the biggest puzzles in current astrophysics is dark matter, which makes up about 27% of the universe's mass. It can't be seen directly because it doesn't give off, absorb, or reflect light. However, the way its gravity affects things that can be seen suggests that it is there. With their strong gravity pull, black holes may give us a new way to study dark matter by showing us how it interacts with normal matter in very harsh conditions. In the same way, dark energy, which is speeding up the growth of the universe, might be connected to things that happen inside or near black holes. The information that the James Webb Space Telescope sent back could hold important clues that can help solve these cosmic puzzles. The finding also makes people wonder what kinds of technology advances could be made by learning more about black holes. The fact that Elon Musk is so excited about the picture of the inside of a black hole shows how science discoveries can lead to new technologies. Musk, the founder of SpaceX, has long pushed for more human space travel. He knows that understanding black holes could lead to new ways of moving things or making energy. Some ideas say that black holes could be used as powerful energy sources because their huge gravity fields make it possible to get energy on a huge scale. This idea is still just a guess, but the picture of the inside of a black hole could be the first step toward looking into these options in more detail. Science fiction stories have often used black holes to show doors to other worlds or even ways to move through time. These thoughts may seem crazy, but they are based on real science speculation. Some people think that wormholes, which are made-up tubes through spacetime, could form when black holes bend spacetime very much. If these kinds of structures do exist, they might provide a faster-than-light route through the world or even lead to trips to other universes. The picture of the inside of a black hole might be the first real evidence to test these ideas, giving us new information about whether wormholes are real or just thoughts. The sense of wonder and awe that this finding brings is one of the best things about it. With their strong gravitational pull and the power to bend time and light, black holes make us question even the most basic ideas we have about how the universe works. People used to think that these things were impossible to get into, but now we can see inside one of them. This shows how creative people can be and how powerful science study can be. The James Webb Space Telescope has already shown that it is one of the most important science tools of our time, and this picture is just the start of what it can do. The James Webb Space Telescope will keep looking at black holes and other strange things in space, getting more information and helping us better understand these strange objects. Scientists from all over the world will be working to look at the data and come up with new ideas to explain what they see. The picture of the inside of a black hole is only one piece of a much bigger puzzle. As we continue to study the world, we will likely find many more amazing things. The joy over this finding also shows how important it is for people to be interested in science. People like Elon Musk and Michio Kaku are very important for explaining hard science ideas to more people and inspiring the next generation of scientists and engineers. The picture of the inside of a black hole has captured people's attention in a way that not many science findings can. It reminds us all of how curious and exploratory people can be. The James Webb Space Telescope's picture of the inside of a black hole is more than just an amazing sight. It is a science breakthrough that takes us to a new area of space and physics that we thought we could never see. As these visual data are put through thorough studies, they will have effects on many areas of study, from astronomy and astrophysics to quantum mechanics and even philosophical ideas about how the world works. Many people were initially interested in the stunning images, but the most important thing about this discovery is that it could lead to completely new ways of thinking about the structure of spacetime, the mechanics of gravity, and the very limits of what humans can understand. To fully understand how big this accomplishment is, it is important to look at how black hole studies have changed over time. Einstein's general theory of relativity first forecast black holes in the early 1900s. Later, they changed from theoretical concepts to real things that could be found by studying how they affected matter around them. Astronomers and scientists have used many tools over the years, from X-ray telescopes to gravitational wave monitors, to figure out if black holes exist and study how they behave. But these detections were always far away. We never saw how the inner parts worked. That has changed thanks to the James Webb Space Telescope, which has amazing sensitivity and can see across a wide range of bands. Scientists can now see inside a black hole thanks to the James Webb Space Telescope. This is the first time that the normal rules of physics don't seem to apply. One of the most important effects of this discovery is that it opens the door to getting direct physical proof for some of theoretical physics's more speculative ideas. For many years, black holes have been used to test some of the most extreme scientific theories, such as those about string theory, quantum gravity, and even the idea of multiple universes. By being able to look straight into the center of a black hole, scientists can test these ideas in ways that were previously unimaginable. For example, in string theory, black holes are thought to be the key to understanding how the universe's most basic building blocks work. The idea behind string theory is that particles are not points but tiny, moving strings at the smallest sizes. Because this idea is so complicated mathematically, it has been hard to test in the real world. However, black holes are perfect places to test these extreme circumstances. Scientists may be able to find signs of quantum changes that would help them figure out if string theory is true by looking at how matter and energy behave as they get closer to the singularity of a black hole. The picture of the inside of a black hole could show how spacetime acts in these situations, which could be the most clear proof of string theory's statements from science. This finding will also help a lot with the study of quantum gravity, which tries to make sense of both general relativity and quantum physics. Modern physics has two main models that explain the structure of the universe on a large scale and how particles behave on the smallest sizes. Attempts to combine them into a single theory that makes sense have failed. A unified theory can really be put to the test in black holes, especially their singularities. The singularity, where the mass of matter goes to infinity, goes against the laws of general relativity. Also, the quantum effects that should control particles in this region have not been found. By giving us a clear view of the space inside a black hole, the James Webb Space Telescope has made it possible for us to learn more about this elusive unified theory. This could be the start of the next big change in physics. This finding could have a huge impact on the idea of spacetime, which is at the heart of both general relativity and quantum physics. The general theory of relativity by Einstein says that spacetime is a four-dimensional cloth that is bent by the presence of matter and energy. In the very harsh conditions inside a black hole, however, this bending gets so strong that space and time are thought to bend in very strange ways. The James Webb picture gives us a unique chance to see these effects happening right now, which gives us new information about how bent spacetime works and how it reacts to the very harsh conditions inside a black hole. Scientists may be able to make new models of spacetime that account for these distortions by studying the exact patterns of light and matter as they interact with the event horizon and singularity of a black hole. This could lead to groundbreaking discoveries about the structure of the universe. In addition to helping us understand how spacetime and gravity work, studying black holes might also give us new ideas about how the world came to be. Some ideas say that black holes may have been very important in the creation of the universe, working as catalysts for the growth of galaxies and stars. A picture of the inside of the black hole might show proof of these processes. This would give us a look into the early universe and help us understand how the complicated structures we see now formed. It would be great if you could like this movie and follow our station. Also, could you leave a comment below and tell us what you think the inside of the black hole will show us? Please let us know what you think. It was fun to watch. See you next time.